Hey everybody, Mr. Field here, and today we're going to be talking about the Pythagorean theorem, what it is, how we can use it, and also we're going to talk about this thing called its converse, which essentially means the reverse. All right, how we can use it to work backwards to solve for something else. So, first and foremost, Pythagorean theorem, it's really important to know it only works in a right triangle. So, in our notes, I'm going to go and fill that right at the bottom note. This is really important. The Pythagorean theorem is a relationship between all three sides in a right triangle. So let's make sure we get that in right off the bat. Little pun there. So again, Pythagorean theorem is a relationship, but before we jump into what that is and how we use it, let's just talk about some of the basics, vocab terms of a right triangle. So a right triangle has only one right angle. Keep in mind, remember, triangle sum theorem tells us that all three angles of the triangle have to add up to 180. So if we have two angles, for instance, that are 90 and 90, well, it's already filled up the entire triangle. So it's not possible to have a 0-degree angle. So a right triangle has only one right angle. The side opposite the right angle, so if we draw an arrow here, that's called the hypotenuse, sometimes abbreviated hype. So I hope you're getting hyped about this video. The hypotenuse is the most important side in a right triangle. Back when we talked about, the basics of triangles, we talked about the relationship between the sides and angles. Well, the largest side should always be straight across from the largest angle, smallest side across the smallest angle. Therefore, since 90 degrees, the right angle is the largest angle, we know the hypotenuse has to be the longest side. Then we call the other two sides are just called the legs. And, ooh, that's badass. Sometimes they will even call one the short leg and one the long leg. In this case, this would be the short leg, just because clearly by looking at it, it's a little bit shorter. And then this would be considered the long leg. But in general, you really just have to know that it's leg, hypotenuse. As long as you make sure that the hypotenuse is the longest side, then we are good to go, the side that's across from the right angle. So there's the basics. Now, the Pythagorean theorem itself, right, states that the sum of the sum of the squares of the leg equals the square of the hypotenuse, which is kind of a fancy way of just saying, hey, if I take the length of A and I square it plus B and I square it, it should equal C squared. Just going back to the picture real quick, it doesn't matter which one you call A or B. Typically, people call the short leg A and the long leg B, but it doesn't really matter as long as you don't mess up the most important one, C. All right, C has to be the hypotenuse, represent the hypotenuse to be the longest side. So we have A squared plus B squared equals C squared. It's just simply a relationship where if you add up A and B and square them, right? A squared plus B squared, it should equal C squared. And this works for every single right triangle. So sometimes it might just ask you to solve for a missing side length. Sometimes it might ask you to say, is this a right triangle? Well, we can use the Pythagorean theorem to do both of those things. So let's check out a couple of examples. So it looks like in this case we have an unknown variable, and I'm going to label my sides. It doesn't really matter which one you call A, B, and C, but I'm going to call it A, then B, and then of course our X is our C. So it looks like we're solving for the length of the hypotenuse. It's always good to take stock of what you're given versus what you're looking for. In this case, example 1, we're given A and B, we're looking for C, the length of the hypotenuse. So I know if I do 9 squared plus 12 squared, right, A squared plus B squared, it better equal, in this case, we're going to call it X squared. That's representing our C. So I'm thinking, well, 9 squared is 81, plus 144, that's 12 squared, should equal X squared. So I'm going to get out my handy-dandy calculator, make sure I add 81 and 144. I'm thinking I get something in the 5. So 81 plus 144, boom, and we get 225. So we have 225 is equal to X squared. Keep in mind, I'm used to seeing it reversed, so I'm going to flip it the other way and say X squared, because I like my variables to the left, equals 225. So from here, we have to ask ourselves, how do we get X by itself? Well, X, we ask myself first, what's happening to X? It looks like it's being squared. The opposite of squaring is the square root. And whenever we do to one side in an equation, we must do the other to keep it balanced. So we should get X is equal to the square root of 225. So we can type that in our calculator. I just want to show you how to do it. Second root 225, and I think we get a nice pretty whole number of 15, which, by the way, in this section won't always be the case. So we end up with the square root of 25, which ends up being 15. Now, just some common sense. Let's check to make sure our answer makes sense. Looks like the A value was 9. The B value is 12. Well, remember, this has to be, because it's across from the right angle, because it's representing the C value, also known as the hypotenuse, it has to be the longest side. And looks like C is equal to 15. So it looks like everything's A-okay. And it checks out. All right, let's check out example 2, which I think is getting a little bit more difficult now, but nothing we can't handle. So the first step, again, I like to take stock. Okay, it's saying this is a right triangle. Technically, I guess it really isn't, is it? We really should put that in there, just because it looks like one doesn't mean it is, but we're going to go ahead and say, yes, this is a right triangle. So we're going to label A, B, uh-oh, that looks scary. And then, of course, looks like we're looking for the C value again. So we know if we do A squared plus B squared, it better equal C squared. Keep in mind, they're giving us a radical now, 2 root 26, or 2 times the square root of 26. So we've dealt with this before. We've talked about this in Algebra 1, Algebra 2. So hopefully it's nothing you can't handle. So we're going to say 14 squared plus 2 root 26 squared equals C squared, which looks like is X squared in this case. Now, 14 times 14 should be 196. Plus, here's the interesting part. Now, if you know how to do this, you don't have to show the full thing, but remember, math is a language. Squaring means multiply by itself. So it's really 2 root 26 times 2 root 26. And when we're multiplying radicals, we end up doing outside times outside, inside times inside. So we're going to do 2 times 2, which should get us 4 root whatever 26 times 26 is, which is going to be quite a large number. However, we want to work smarter, not harder. A lot of you probably would multiply that and get some number, right, in the 400 to 500 range. However, or actually, I think it's a little bigger than that, pardon. So you know what, for the sake of the video, let's find out. 25 times 25, I think is 6.5, so 26 times 26. Yeah, 676. So a lot of you would do that. But again, I want to work smarter, not harder. This whole thing, right, we squared it, is really just 26 times 26. So a lot of you might write it as 4, where I'll do this off to the side, 625, and then realize, well, a lot of the times they're going to want this in what's called simplest radical form. So remember these simplifying radicals, we have to do these little factor trees. So like, I don't know, 625, I know 5 goes into it because it ends in 5, so we have to start looking for factors. So like, let's think, 625, I know 25 goes into it, so 625 divided by 25 looks like we get, well, look at that, 25. So it should be a perfect square. So that is one way to do it. Oh, shoot. Everybody, I'm making a silly mistake. Come on, Field. Let's go back. It's not, it's 26, it's 676. All right, that was weird. 676. I'm writing the wrong numbers down, folks. So 676. So we'd have to break that down. However, we already have it broken down right here. Notice 26 times 26 under the root. Well, that's already a pair. Since this is a square root, we know that we already have a 4 out front. And then because we found one group of 26s, 126 can come out, and then nothing gets stuck. So we just got to do 4 times 26, and then add that to 196, and then that equals the square. Sorry for that explanation. Kind of went awry there. My point is, you can multiply these together and get 676, and then start breaking down, like over here. But you're going to arrive at the same answer. 26 times 26, that's already a pair. So we might as well just, circle it and bring it out. And then 4 times 26, let's see what that is, just to be sure. I'm making mistakes already, so let's keep cruising. 104. So it looks like we're going to add 196 to 104. 196 plus 104 equals x squared. Well, 4 gets me 200 if I add the 4 to 196. So it should be x squared equals 300. The opposite of squaring is the square root, whatever you do one side or the other. And we get x equals whatever the square root of 300 is. Now, depending on the directions, it might say, hey, you can just type this in your calculator and get a decimal. However, I'm thinking we probably want it in simplest radical form. So we can break this down. I know it's going to be 3 times 100, right, is 300. And I know 100 is 10 times 10. Now, could I write those 10s then more? Of course, but since it's a square root, I'm looking for groups of 2. So it looks like we found one group of 10, so a 10 will come out, root, to represent that group, and whatever got stuck, which looks like 3. So I think the final answer would be x equals 10 root 3. for our hypotenuse. And again, you could check. You could just literally type in 10 root 3 or 10 times root 3 in your calculator, and that would give you the length of the c value, or x. And then you could type in 2 root 26 and then get that decimal version to make sure that, in fact, the x should be larger, and it is. All right, but for the sake of the video, I'm going to keep cruising. Now we have this one. So it looks like I'm going to label again A, B, and it doesn't really matter which one's A and B. Yours might be slightly different. They're interchangeable as long as you don't mess up the c value. So once we have the c value set up, we can know that we have y squared, or a squared, plus 10 squared, which I'm hoping you're cool with me just writing 100. We already know it's going to be 100, equals 12 squared, which is 144. So in this case, we're going to subtract 100 because our goal is to get y by itself. We have y squared equals 44. Opposite squaring, square root, bada bing, bada boom. Y equals whatever the square root of 44 is. Now, I'm going to go ahead and write it in simplest radical form. I know that's 2 and 22, 2 and 11. So it looks like I found a pair of 2's. So 2 comes out. Root. What didn't find a partner? Well, that lonely little 11. Keep in mind the 22 didn't make it. Got broken down. So when we did use one of its parts, so we can't include that in our answer. So it should be y equals 2 root 11. So just make sure you're paying attention to the directions. Sometimes it's, and most of the time in this section, it's going to say simplest radical form. For instance, like 2 root 11, 10 root 3. They don't always work out to be nice, pretty whole numbers. And a lot of the times we're not looking for the decimal answer in this version, in this section. So take a moment, pause the video, try the you try problem, and see what you know. All right, hope you got a chance to try the you try problem. For the sake of time, I'm going to keep going. All right, so the converse of the Pythagorean theorem is what we're going to talk about next. The Pythagorean theorem essentially is using the Pythagorean theorem backwards in order to determine whether a triangle is a right triangle, whether it's acute, or whether it's obtuse. And in this case, the most important part of the Pythagorean theorem, we're thinking a squared plus b squared equals c squared, right, is c. C is the most important side. It's the hypotenuse. It's the one you can't mess up, right? So in this case, if the angle is a right triangle, the converse tells us, well, c squared will be equal to a squared plus b squared. Shouldn't really be a shocker. That means it follows the Pythagorean theorem. If you square a, square b, add them up, it better equal c squared. However, if c squared is smaller, remember c squared is the important part here. If c squared is smaller than a squared plus b squared, we know that it's going to be an acute triangle. And of course, the opposite of that is c squared is greater than a squared plus b squared. We know this is an obtuse triangle. So we can use this in order to determine what type of triangle we've got going on. So first thing I'm going to do is we're wondering, okay, is this the right triangle? Just because it looks like it doesn't mean we know for sure. So let's check it out. I know that if this was indeed maybe the right angle, question mark, this would have to be the hypotenuse. It has to be C, and from there it doesn't matter which one we call A and B. So I'm thinking 12 squared plus 9 squared should equal 17 squared, which would be 144 plus 81 equals, I want to say that's 289. Let's just check with our handy dandy calculator to be safe. 17 times 17, 289. And we already did this kind of earlier. We know that, pardon, find a problem. There we go. 144 plus 81. Well, we did that earlier. 144 plus 81, so we should get the same result of 225. So we're going to be comparing 225 versus 289. Now keep in mind, the trickiest part of these problems is, notice when I rewrote these, c squared was to the left. So we want to make sure we do that as well. So we're going to flip-flop this. This was the 289, this was the c. So 289 is something to 225. Hopefully you would agree is greater than. Therefore, we know c squared, since it's greater than, this should be an obtuse triangle. So it may look like it's a right triangle, but maybe it's a little bit more. Maybe it's only like 91 or 92 degrees. Maybe it's just slightly obtuse. So what I'd like you to do is use this and check out the next two examples real quick, the example 4 and the you try. Test yourself, see if you can determine, especially with that radical in there, what type of triangles we got going on using the converse of the Pythagorean theorem. Thanks for watching.